Nuts and bolts. Finally, Jeff, just tell us nuts and bolts. What's this mean? So if I have, what's the derivative? I just erased the question about it. What's the derivative of ln x?
1 over x.
And when we do that, what we're actually hiding is this. And that's kind of implied. You don't actually have to write that down because the minute you write ln x, it's understood that x has to be. But if you start to work with that, you take the derivative, and then later you start to work with this, you'll forget that it's got to be greater than 0 to make sense. You kind of with me? Because that function came from the derivative of a function that can't exist 0 or below. You guys kind of with me? So this is still true. This is always implied the minute you write that down. So that statement is still true. But this is somehow, in a way, more complete. It captures the other side. There's no need for this because what's this guy? There's only one place where this has a problem, and that has the same problem. So they do completely match. Their domains completely match. So I don't have to restrict a domain. You guys kind of with me? Now let's go back for a second. That makes this problem a lot easier. It wasn't quite the same kind of problem I thought because it involves ln. ln has this weird little thing with absolute values. Does that somewhat make some sense? And they do discuss this in the book a little bit, page 220. And they break it up into piecewise function, and they kind of prove it. So the problem was, what was the problem? Cosine x in there? Cosine of another. So now this problem is a lot easier. Because the derivative of ln absolute value of something is just 1 over that thing times
Negative sign of that thing.
the derivative of that thing. Cool, right? And what rule did I just apply? Chain rule. I love it. Have something inside of an ln. The absolute values actually end up not messing you up because it's a more complete picture of ln. It allows for the other side of the picture that 1 over x represents. Or 1 over whatever the hell.
So if that wasn't ln, it would be more complex. If the
Yes. Yes. And in that case, they'd have to give you some further information, or you have to really treat it piecewise.
Okay.
Yeah. There was a problem. Somebody came to me with a problem about absolute value, but it was more specific. I don't know if I could see it right away, but...
It was a movement for it.
3, 4?
Yeah. Those are... number 56.
56, there it is. Good, thank you. So that's ln. ln is completely cool with absolute values. In fact, it's a part of its broader definition. How we doing so far? So this is not wrong. It's just sort of implicitly hiding something, which is what implicit means. It's hiding that x has to be greater than 0. This is a little more complete in a sense. Yes, sir?
Can you finish out the derivative for the cosine?
Oh, so then... derivative of cosine, negative sine of stuff times
1 over x.
good. So then you can collect it, put an x down there, put the negative sign up there. Is that cool?
Sure, yeah.
And you can even make it negative tangent all over x if you want to be all nifty about it. Okay, how are we feeling? I have a feeling that no matter my efforts, tonight is bumming you out more than helping. I don't know. I get that sense, but we'll see. All right. So real quick, this problem, just to look at it, because you all have to do this eventually. So it says y, or this is one that you skipped and just said, I'm not really sure. But now, so it's called a bullet nose curve. So if you try to graph it, and your graphing calculator just have an absolute values function, you can see why it's called that. And it kind of makes sense to you guys. Well, let me do the side stuff. Blah, blah, blah. But look, they give me more specific stuff. They say find the tangent line at 1, 1. So I can rewrite this function in a more explicit sense based on where I know I'm interested in. I know I want my input to be 1, 1. Therefore, the absolute value is going to be
1.
Well, it will eventually, but the absolute value of x in that area is just x. You guys with me? In the area around 1, all my inputs are positive. When I say around 1, it's like when we did the limit tables, 0.9, 1.01. So in the area around 1, the absolute value of x is equal to x, because all your inputs are positive. How we go so far? That's why I can rewrite this. Because of this, I can rewrite this as that. And then you just attack it. You can do you've got a quotient rule there, right? Okay, so that one is not as evil because they give you that more specific information to deal with. Okay, cool. All right. I'm not going to get any reaction out of you at the moment, so I'll just keep going. So, anything else before I get into 3.7 a little bit? No? Okay. All right. So, section 3.7, there's really... 3.7 is like the... 3.7 is not calculus word problems. Those are coming. Right? 3.7 is, they actually give you the equation that you need, and you really basically just need to take derivatives. So 3.7 is like, practice your derivatives, but in a real-world setting. So for example, let me do a couple side examples from here first, and then I want to focus on the main thing I want you to worry about. But one example, like, let's do number... What you got there, Jeff? Number 14 looks neat. Let's see. It says, stone is dropped into a lake. This is section 3.7, by the way. Right. Stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Find the rate at which the area within the circle is increasing, blah, blah, blah. So I'm making this circular, so I got this lake, I threw this stone in there, so it's making these ripples come out. Cool. The ripple is traveling outward at a speed of 60 centimeters per second. Find the rate at which the area within, okay. So if I define a few things, here's my R. What's my area going to be for some arbitrary circle there, of course? Pi r squared. Now the funny thing with this problem is this is a rate problem. Now, do you notice how, looking at the units on the rate they gave me, what am I going to take the derivative with respect to? What will I take the derivative with respect to? With respect, not just with respect to a radius.
Radius to time?
With respect to time. Kind of with me? So really, this 60 centimeters per second, can you identify what that is in symbols? What's changing as it goes out? What's directly changing? I know the area is changing, but what does that 60 directly relate to?
Radius?
The radius, right? 1 second later, the radius is 60 more centimeters than it was before. You with me? Okay, so that's the change in radius with respect to time. I like it. So this is where things get a little interesting. And I didn't realize that they had a problem like this. This is actually more like section 3.9. So I didn't pick out the best problem. I want to take the... and what are they asking me? What's the actual question related to?
Increase in area.
Yeah, find the rate at which the area is increasing. So what's the symbols for that question? How do you write the symbols for that question? The rate at which the area is increasing.
dA,
Good. The change in area,
DR.
dt.
dt, with respect to time. You with me? So here's, I should have picked this one, but we're getting this a little too early. But I want to take the derivative with respect to time for both sides. So I'll do this one. That's dA dt. Now, for example, what's the derivative of y with respect to x? Or even better, what's the derivative of y squared with respect to x? This is that implicit differentiation we were doing before, right? 2y
2y
dy dx. So what's the derivative of r squared with respect to time?
2r
2r dr dt. And what's dr dt? 60. To see how it all comes together. So they tell me this. That's the symbol for what they told me. They ask me this. That's the symbol for what they ask me. So the connection there is the dt. I gotta take the derivative with respect to dt so I can plug this stuff in. So I know that dA dt equals pi times 2r dr dt. And now I can plug that in there and solve for dA dt. So that's the next level of implicit differentiation. It's something called related rates. I actually didn't realize they snuck one of those problems in there until I picked it to do.
So the area would be in terms of r.
Second,
The area will, the change in area will be with respect to r.
which makes
In
sense,
terms of
right? The units have to be, what would the units be on dA dt?
centimeter squared. Or
Good. Centimeter squared per second. Right? And I do have centimeter times centimeters. So I will have centimeter squared at the end. You with me? So now you just got to plug it in. dA dt equals 2 pi. Now the interesting thing is r. What is r? Oh, okay. They give it to us, basically. Part A says 1 second later. Right? After 1 second, what's r going to be? 60. Because after 1 second, it's gone 60 centimeters out. So for part A, I would have dA dt equals 2 pi. Later. R is 60 because it's been 1 second, 60 centimeters. And dr dt is always this. Well, I don't need to put all the unit there. So 60, 60. You guys got it with me? Okay. All right. So let's do one more from that section because that one is actually one from section 3.9. Section 3.9 is going to be all about this, and you can see why it's called related rates. It's relationship between two rates. So math people being very creative. Those related rates.
So how important this section is?
No. I want you to realize 3.9 is stupid important. 3.7 is stupid important. Just for some reason they snuck a 3.9 problem into 3.7. And this is something you can definitely do. This is just implicit differentiation, but it's weird because it's involving a variable that's not explicit anywhere. So both A and R are implicit functions of time. Because if I wait some time, R is going to grow and A is going to grow. They both depend on time. So we normally have at least the variable taking respect to is normally somewhere in there. The X is somewhere. You with me? Related rates is they both are functions of some hidden variable. Very often it's time. So let's do one more of these. In fact, I might as well do a freebie for you. Blah, blah, blah. Oh, okay. Well, 15 is more right. And I know it's one of your home problems, but we might as well do it. 15 is more what you should expect from these kind of problems. A spherical balloon is being inflated. Find the rate of increase of the surface area with respect to the radius r when r is blah, blah, blah. So first off, somebody help me out. Surface area, well, they tell it to you. I was going to ask if you knew. And real quick, what's the volume of a balloon? Of a sphere?
4.
4/3 pi r cubed.
Good, 4/3 pi r cubed. Somebody help me out. What's the derivative of that?
3r squared. 4 pi r squared. All this stuff.
4 pi r squared.
Which is the surface area? Because if I increase the radius, now go with me for a second, right? Because this is basically dV/dr, right? Let me let you absorb that for a second. Come on, this is kind of cool. Go with me. If I have a sphere and I have a radius and I increase the radius by just a little bit, I mean just a stupid little bit, it's like taking this and wrapping and putting like a layer of Gorilla Tape on it, or whatever tape you want to use. Are you with me? Isn't the volume going to increase by just a little bit? I mean, that tape, how thick is it? It's actually pretty good. But it's not very thick, right? It's barely there. You with me? Maybe some Scotch tape. Just put Scotch tape all around it because you're just insane sitting in your room taping balloons. I don't know what you're doing. But that volume, whatever the volume was, is going to increase by basically the surface area. Because you just put a surface area on it. And then you can do another surface area and another surface area. So that's why it makes sense that the derivative of the volume is equal to the freaking surface area. Just like area of a circle is pi r squared, what's its derivative?
2 pi r.
Which is the circumference. You just keep adding circumference on the outside to change the area, changes a little bit, but you wrap the thing around the circumference, you just add another circumference on top. That's how much the area is going to change by. It's really kind of a neat idea. You have to know all that? No. So here I know that surface area is 4 pi r squared. And they ask me, blah, blah, blah. Find the rate of increase of the surface area when r is those things. Okay. So they ask me ds. What are they asking for? ds, the rate of change of the surface area with respect to the radius. So dr. So what is ds dr?
8 pi
8
r
pi
dr.
What would it be? I like that. Let's go with it. 8 pi r dr. What am I taking respect to?
Yes.
dr.
For this one?
So that's gone. Yeah. When I'm taking the derivative with respect to that variable, that's when I don't really need the chain rule to show up because it's direct differentiation, right? This one, I take the derivative of some function of r with respect to time. So I had to have a dr dt show up. When I take it with respect to dr over dr is 1. Kick ass.
Why is it dr over dr?
Because what am I taking it with respect to? I'm taking the derivative of the surface area with respect to r. That's what they tell me, right? So then if I do apply the chain rule, it would be the derivative of the inside function with respect to the variable I'm taking the derivative of.
Oh, okay, so yeah.
dr. That's gone. That kicks ass. So then now it's easy as hell. Now I know exactly how the surface area is changing with r. So when they tell me that it's 1 foot, just put the 1 in for r. Now this problem is just too damn easy. Right? So this is what I'm talking about. You got these little side issues that part of me wishes you guys didn't worry about at all. But it's good to look at them and see why you don't have to worry about them at all. So that's what some of these problems are going to be like the problems starting at number 12 and on. The first few problems are going to be about this. And this is the one that I'll definitely have a full problem on the next test. Like number, let's see which one, doesn't matter. Number 2, I guess, that looks fine. So number 2 on page 233. Where'd it go? 0.0104 minus 104 t cubed. Okay. So be very careful. All the instructions are above that, right? Part A through I. Oh, yeah. Blah, 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 blah. Yeah, okay, good. So they tell you up at the very top, S equals this. And whenever you see that letter S, it pretty much means the position function normally. Right? So that's the position of this particle. Right? So for example, at time 0, where's the particle? At 0, right? And they should tell me what units I'm dealing with. T is in seconds, S is in feet. So physics professors would hate this because feet, of course,
Unmeasured.
based on the actual foot of King Henry. Yeah. And we had the whole Tea Party thing and all that kind of crap, but we're still. I don't mean the Tea Party, the party, political party. No. That's a whole other thing. All right. If you're a member, I'm sorry. For so many reasons. So let this be easy. If I'm given a position function, how do I find the velocity function?
You take the derivative of the position.
Right? Is that equal that? Because the velocity is just the rate of change of position, and that should automatically now tell me take a derivative. That's the rate of change. So very first thing I do with this kind of problem is figure out what the velocity function is.
104 t
Yep, 104 t cubed.
minus 0.12 t squared.
Is that cool? Just nice power rule again, I love it. And then the acceleration function would be
0.12 t squared minus 0.24 t.
is everybody with me? Okay, it's that simple. I can always find velocity and acceleration by taking derivatives of the position function. The position function will not always be nice. The position function might involve some ugly stuff, but I just take the derivatives. So then I'm going to ask you questions like this. Find the velocity at time t. Okay, I did that. That's part A. The velocity at time t is this. Don't let that question freak you out. Just take the derivative and you've got the velocity at any time. Part B says, what's the velocity after 3 seconds? I mean, now I can see how several of these steps are going to be really easy. Once you do the derivatives, you have the functions, you just have to plug this stuff in. What you really got to be careful about is what I was talking about earlier. What's the velocity at 3 seconds versus when is the velocity 3? In this case, feet per second. You with me? One involves plugging a 3 in, the other one involves setting it equal to 3. You're going to get both. If I plug a 3 in there, I'll get something. I don't know.
Good enough.
So we have now.
Do that on a test, just math.
Well, let's see. 142 squared, 0.36 times. Is it 0?
Yeah, it's 0.
Okay, thank you. Feet per second. And trust me now, on the test, if you don't put units down, I will take points off. Right? Oh, yeah. But it's not even that. It's just that's the appropriate way to answer this question. Right? C, when is the particle at rest? This is a perfect example of translating the question into something that makes more sense, translating it into more mathish, pseudo-math. Particle at rest means it's...
Velocity 0.
Yeah, I love it. It's not moving, so velocity is 0. So if I set that equals 0, I already know it's at 3, and I already know it's at 0. And there's at most 3, so I only got 1. So what do I do with this?
T squared. 0.04.
So one thing, do you realize I could just do this?
Can multiply by 100.
Yeah. Good. Right? You're all like, yeah, you just erase them. Yeah, great. So if I multiply both sides by 100 in school, divide by 4, so I get t cubed minus 3t squared, and then
T squared.
t squared,
T minus 3.
and then I get the two answers we already knew.
T are 0
T is 0
or 3.
or 3. I like it. So we already knew the 3 answer. We already knew the 0 answer, basically, because they're both make it 0. We just didn't realize that there were no other answers until now.
Did you just factor out the 4?
Yeah, so you're cool with the points going away? And then I divided by 4.
Oh, okay.
That's the beautiful thing about being equal to 0. 0 just eats it up. Eats up constants. Part D is a little more interesting. Part D says, when is the particle moving in the positive direction?
The velocity positive.
All right, so the velocity has to be greater than 0, right? You guys kind of with me? The velocity is a cubic function. We already know where its roots are, right? What are the roots of the velocity function? 0 and 3, right? So I know it's 0 at 0 and 0 at 3. So now I just got to figure out, this should feel very familiar. And what's the multiplicity of the 0?
What was that?
What's the multiplicity of the 0? Of the 0, 0. 0 showed up twice, right? So it's multiplicity 2. I don't know what that has to do with you. Yes, I do. It's how I can tell where the sign's going to change. So is this at all familiar to you guys? You should have done this like crazy in pre-calc. If I plug a 1 in, what do I get for the velocity? What kind of value?
Negative.
Yeah, I get 0.04 minus 0.12, so it's negative. So it's going to be negative in here. And the beautiful thing about the multiplicity tells you it's going to act like a parabola at 0 because it's squared at 0, so it's an even power there. So it's going to stay the same sign. Now on this side it doesn't make much sense necessarily because it's negative time, but you launch rockets with negative time. I'll give you that. T minus really does mean negative time. It hasn't gone up yet. But that probably doesn't come into play in this problem. And up here, around 3, it's multiplicity 1. It's going to be like a straight line. It's going to go through, so it's going to change signs. So where's the velocity? Positive? Greater than 3. And it doesn't say anything about... Yeah, it does. At the very top, it says t greater than or equal to 0. So you don't have to worry about this part. So where's it moving? It's t greater than 3. I love it. Because at 3, of course, it is not moving. So you don't want to include that. All right, so this guy starts and he goes backwards. And he's like, oh, shit. And then about 3 seconds later, he finally gets moving in the positive direction. Yes?
On C, do we have to like plug it into units?
Oh, get your seconds on there. That's cool. Yeah. Part E says... Oh, now here's where we get a little bit freaky. The mistake that people make of Part E. Part E is the only one of these that's really difficult. And I'm hoping you realize, nothing we've done here so far is really, really difficult. I don't know if you guys agree with me or not, because I can't read you worth anything. Never play poker with you guys. E is the weird one, because it says find the total distance traveled. And the mistake people make is they'll just do, okay, total distance at 8 seconds. Let me just plug an 8 in here. And that's completely wrong. Because that function tells you where it is. It doesn't tell you how far it's traveled. Because what did this guy do at first? He went back. He traveled back some ways. And then he had to travel that back just to get to the 0 point again. And then he went forward. So the total distance he traveled is not going to be equal to where he is at 8 seconds. You got to add in all this back and forth shit he did here. You guys kind of with me? Yeah. Okay. So here's the way, I kind of like the way the book did this, and I can't even remember the way I used to do this, but at 0 seconds, he's going backwards. And how do you figure out, well, let's see, I don't want to do this. Maybe there's a better way to do this. Yeah, let me see. Page 225. You have to be a little liberal with your what am I trying to say? Your scale, your representation of where we are. So it's equal to 0, and we're actually going to have to go backwards a bit. That's right. So let me put t equal to 0 here. T equals 0 on there. And then at t equals 3 is where I turn around. Is that cool? Because that's where I go to 0 velocity. That's where I actually turn around. So at t equal to 3. So I'm going to go backwards somewhat. At t equal to 3, I'm going to turn around. And then I want to know at t equal to 8, how far have I gone total? So if you do f of 8, you're just going to get this piece. It's just going to tell you from 0 to there, where are you now? It's not going to tell you how far you've actually gone. So how the hell am I going to do this then? There's only one value you really need to get to add on top of this in a certain way. So that only gives me this much, right? That's f of 8.
6 minutes?
Yeah, f of 3.
6
So you
seconds?
do f of 3 minus, or f of 8 minus f of 3.
Yeah, you got to add here, right? Because he's going more distance than just this. He actually does this, whatever this distance is, whatever f of 3 is, he does that twice. Good. So it's really, and I got to be a little careful. In the background of this problem is the fact that at 0, what position am I at?
0.
0. Got it with me? So it really, really is f of 8 minus f of 0. That's this piece. Right? And this could be absolute value, but you don't have to make it all that kind of crap. I'm trying to make you guys really see what's important. How far this is, the difference between where he started and the position he ends up at, plus this extra piece. And how do you find that extra piece? By seeing where he turns around. So how far, where is he at 3 seconds? Where is he? What's f of 3? Whatever this is. No, we plugged in 3 into the velocity and we got 0. Got to be careful. That's where he turned around. It can't be 0 because he starts at 0 and up until 3 seconds he's going backwards. It's got to be negative. Good. Maybe somebody could really figure out exactly what it is. So we'll get 0.81. Is that cool? 3 to the 4th is 81. So 0.81 minus 27 times 4 is 27 more than that. So negative 0.27. I like that. So it's negative 0.27 feet. You with me? Now the negative is just the position. The distance, of course, is the absolute value of that. So I have to add this 0.27. He went backwards 0.27. He's, oh shit. Turn around now. He went forward 0.27 just to get back to here. And then he went this far from there. Yes, sir?
So it would be f of 8 plus 0.54.
Yeah, so it would be f of 8 plus twice absolute value of f of 3. And there's no, I hesitate to make a general procedure for this, putting absolute values over every damn thing. You just have to think about it like that. Where do I start? How far does the position function take me? And then adding in the part where he turns around. Add in 2 of that, because he's got to go back and then come back around.
Can we add 6 minutes to 8? 3 by 3, then 8.
And then make f of 14?
Yeah.
No, because this is not a linear function, so you can't. Doing something to the inputs doesn't make the corresponding change in the output. I don't know how else to say that. So you can't just do that. You have to actually look at the positions where he is. You have to use the function separately. You can't just change the inputs. Yeah?
Do we have to add the 0.27 twice because of multiplicity of 0?
No. I want to be real careful.
Okay.
If I want to know how far this guy went, he went 0.27 up to 3 seconds, right?
Right.
Back, because it's negative. And then just to get back to where he started, he has to go to 0.27 again. Now the whole reason I did that is because f of 8 tells me this distance. That's the whole thing. So that's why I double. If you could have the same problem, but somebody went forward and then back and then ended up somewhere. So you got to take this distance, whatever this distance is, and double it.
Okay.
And then add it onto this distance.
Just because multiplicity is just coincidence, right?
Exactly. Complete coincidence. Well, in a way, you've got to have that turn happening somewhere, so you will have that. But it has nothing to do with why we doubled it.
Okay.
Yeah. Okay. And they have a completely worked out a problem on page 224 with all the different parts to it. So that's the kind of problem I'm going to put on the test. Part A through whatever. Yeah.
So we just have to pay a lot of attention to the fact that it could go backwards. We have to know it's basically off of
This guy. If I didn't do this guy, I could never draw that.
Okay.
Right? Because I know he's going backwards, and then he turns, and then he's going forwards. You with me? That's what told me exactly how to draw that. And that drawing helped me figure out what to do here.
Okay.
Yes?
Are these kind of problems more straightforward with trig? Almost considering they already have that built-in oscillation kind of deal where you go back and forth.
And with a trig function, you actually get this. You could start part of the way through a period, so it actually ends up looking the same because you'll stop, and if you kept going, you would actually get this, the complete thing. But it's just going to stop somewhere, and then it feels like the same problem in a way because you're kind of going back on yourself and coming.
So it's really the same process.
Yeah. Now it'd be really evil if they did this a few times, and then you're like, and then they stop some arbitrary. Oh, screw it.
Yeah.
Right. Yeah.
Was V of t as greater than 0 given, or how do we know it's greater than 0?
Oh, that's the question. That's how we translated the question. When is it moving in the positive direction? When the velocity is bigger than 0. Physics always says the sign on something just tells me the direction. Doesn't always say that, but most of it is the direction this thing is acting in.
So you can't use like a physics distance formula at all for anything? Like physics doesn't have any distance formulas you can utilize for that? Like I know they had was it initial velocity times time plus, was it 0.85 with acceleration squared, or time squared?
So you're thinking about kinematics in a gravitational field, and this is just...
You can't use that, okay.
Yeah, well, actually, it's not even just gravitational field, but you have to... The acceleration here is not constant for one thing.
Oh, okay.
So do you see what I'm saying? So it's going to have all these. You could create a function,
Okay.
but your v and your a in that equation would not be constants.
Okay.
Yeah, does that make sense?
Yes.
Normally in the physics they kind of have an initial velocity and the acceleration is constant,
Yeah.
right?
because then it's-
I can immediately make that worse if I say the acceleration is not constant.
Okay.
Yeah.
Yeah.
Okay, cool. But it would work, to tell you honestly, if you put that function dependence in there for the acceleration. Yeah, that'd be kind of neat to do. Okay. So really, what's kind of cool about tonight is we got a little preview of section 3.9. 3.9, and to give you a little look into the, backstage at Grossmont College, is they emailed us. Sean Hicks is the Math Studies Center coordinator. I used to do that a few years back, but he emailed us and said, I want to train my tutors on the related rate stuff. Because a lot of the tutors, they took calculus, a year, 2 years ago. It kind of leaks out your head. So with the stats tutors and with the calc tutors, so he was asking us, when are you going to be in related rates? So I just want you to realize it's that kind of thing. It's not crazy hard. It's just that they want to be ready because they know you're going to be coming at some point with questions about related rates. Related rates just get weird, and we're just not used to. I mean, that one problem was definitely very strange. We're not used to taking derivative with respect to something I don't even see in the equation at all. It's that hidden variable. Yeah.
I just got a quick question on the very last thing that you wrote, FA plus 2 absolute value of F of 3. Why did we get that?
And I wrote that just to write something to represent what I was doing. I don't worry about absolute values, really. I don't want to, I hate doing this kind of problem and trying to figure out a general way to express it. It's just, I went back to 0.27. And I know that from, where's the negative points there? It was negative 0.27, but I'm not going to use the negative, because that's the distance I went was 0.27 feet backwards. That's all the negative means. So that's why the absolute values are going to show up when you look at the example. But just realize they're just saying it's 0.27 back, so it's 0.27 that way to get back. So it's twice 0.27, not negative 0.27.
Where'd you find 0.27 apply to F of t?
F of 3.
F of 3.
Yeah, because 3, why was 3 so important? Because that's the point where I turn.
Started turning, yeah.
Exactly. So I want to know how far back that is, so I know double that will get me back to where I started. Cool. Okay. This is a good place to stop. We're going to focus next time on related rates, and we're going to get into section 310 a little bit next time. Also, next time, if you realize, when is your next test?
2 weeks.
Yeah, the 19th. So next Wednesday, I'll have the practice test for you, right? Next Monday, I want to have a quiz. See if I catch people. Vlad, careful. Quiz section 3536. For Monday. Yeah. Don't worry.
Coming Monday?
Did you already have the other class?
Yes.
This is for Jason, not the one coming, the one after, right before the test, right?
Next Monday, meaning the one coming. Yeah. Today is today's Wednesday, so next class we're having this quiz. Yeah.
Joshua?
Good. Okay. Make corrections just like anything else.
Okay.
Right.
Can do.
And we started off the class doing some corrections and talking about some stuff. Unfortunately, I didn't tape.
So, that's okay. Yeah.